Okay, we'll start now. So, if you are having any issues with my voice or any other noise, I mean, if there is some noise outside, so if that noise is too much, please let me know. Okay, we'll start now. I'm audible. If not, please let me know. Okay, so we'll start now. I welcome you all back for the problem solving session 8, and this course is Fluid and Particle Mechanics. So the course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering, IIT Madras. And the live sessions are handled by myself, Ankara Kartika, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So this course is Fluid and Particle Mechanics, NPTEL course, and with the course code NOC 25CH49. And as we all know, this is a 12 weeks course, and it is about fluid mechanics coupled with particle mechanics. So we have seen almost all the basic things with introduction to Navier-Stokes equations and their exact solutions, dimensional analysis, and introduction to particles. So packed bed and fluidized beds and filtration. So books and references, we have Unit Operations of Chemical Engineering by Warren Lee McCabe, Julian Cleveland Smith, Peter Harriot, and second is Fluid Mechanics by Frank M. White, and third is Introduction to Particle Technology by Martin J. Rhodes. So few references are Coulson and Richardson's Chemical Engineering, Fluid Mechanics by Piyush K. Kundu, and Principles of Colloid and Surface Chemistry by Paul C. Hemans and Rajagopalan. So week 8, the content is about pressure drop through packed bed, which is continued from last week, and starting with fluidized bed and filtration. So we'll be solving problems based on fluidized bed and filtration in today's class. The theory for the same is taken by the professors in the NPTEL lecture videos, so you may refer that. And by now we all are familiar with that. So let us move on to the problems directly. Okay. So first one is a problem on filtration. So the question goes something like, a leaf filter has an area of 1.2 meters square and operates at a constant pressure drop of 300 kilopascal and produces the following results during a test on filtration of a slurry. So the time in seconds is given as 300, 600, 900, 1200, 1500 and 1800. Basically it starts from 5 minutes and goes up to 5 6. Okay, no, 5 10 15 25 5, and this is 10 and this is 15 and this is 20 and this is 25 and this is 30. So time is given in seconds, and if we convert in minutes, it is like from 5 minutes to 30 minutes. And volume of filtrate collected in meter cube is given as 0.2 meter cube for 300 seconds and 0.3 meter cube for 600 seconds, 0.4 meter cube for 900 seconds, and 0.5 meter cube at 1200 seconds, and 0.6 meter cube 1500 seconds, and zero point 0.8 meter cube at 1800 seconds. And we are asked to assume the cake is incompressible. Evaluate the slope and intercept required for the calculation of specific cake resistance and filter medium resistance. For slope calculation, use the 2-point formula. 2-point form. So we are given the volume of filtrate collected in meter cubes at different times, and the leaf filter area is given as 1.2 meter square, and it is operating at a constant pressure drop of 300 kilopascal. So now we have to evaluate the slope and intercept required for the calculation of specific cake resistance and filter medium resistance. RM for the filter medium resistance. So we'll see how to do. First we'll write what is given, and time is given in seconds and volume is given in meter cube. So we'll come back to this later. So when analyzing the filtration at a constant pressure, the integrated form of the filtration equation is T by V is equal to mu alpha CV by 2A square delta P plus mu into Rm by A into delta P. So if we take it, so we'll be having slope and intercept. It is basically in the form y is equal to mx plus c. So y is t by v and x here is v. So m, that is mu alpha c by 2a square delta p, is the slope, and this mu rm by a delta p is the intercept. So t is the time and v is the volume of the filtrate, and mu is the fluid viscosity, and alpha is the specific cake resistance, and c is the mass of solids per unit volume of the filtrate, and delta p is the pressure drop, and a is the filter surface area, and here Rm is the filter medium resistance. So when we know slope and the intercept, we can get the alpha and Rm, so that is specific cake resistance and filter medium resistance. So now we have to find out slope and intercept. So how can we find the slope and intercept? What we can do is we can plot T by V versus V. So we can plot T by V versus V, that will give us y versus x. So y is equal to mx plus c, and m will give us, m is the slope which is equal to this, and c is again the intercept which is this. So if we plot T by V versus V, and we can get the slope and the intercept. So rather by in the question what is given, we are given only the filter surface area. We are not given anything else. So what we can do is, we for that only we have T by V versus V as I mentioned. So in the question we have only time and volume. So now we have to calculate the T by V. So we are taking, this is time and this is volume. So we are dividing T by V. So 300 divided by 0.2, that is 1500, and 600 divided by 0.3, that is 2000, 900 divided by 0.4, 2250, 1200 divided by 0.5, 2400, and 1500 divided by 0.6, that is 2500, and 1800 divided by 0.65, that is 2769.223. So now plotting T by V versus V will give us the slope and the intercept that we know. So how else can we get, that is the, because we don't know M and C, we cannot calculate by using the slope and the intercept formula. But what we can do is, 1 minus y2 is equal to 1 into x1 minus x2. So I'll show you the basic thing. Or yeah, as we were talking, it is y is equal to, or else y is equal to mx plus c. Now let us consider one point, y1 equal to m x1 plus c. M and c are constant for that particular line of equation. See. So M and C doesn't change because slope and intercept is constant for throughout the points. It is like graph. Like if we plot a graph, we will have the same intercept and slope, but then points, even though the points are varying, right? So that is what is given here. Y is equal to y1 mx plus c. Okay. Mathematically, this is the formula. Mathematically, y is equal to mx plus c, y1 is equal to mx1 plus c, and y2 is equal to mx2 plus c. Now what we can do, y2 minus y1 equal to m of x2 minus x1. Okay. So just we are subtracting this from this one from this one. So y2 minus y1, y2 minus y1 is equal to m, we taken as common, x2 minus x1, and cc gets cancelled. Now m is equal to y2 minus y1 divided by, this is what we do, right? What is slope? It is like dy by dx is the slope. So here we are doing t by v, that is y. So t by v 2 minus t by v1 divided by v2 minus v1. So this is how we got this. So it is just dy by dx. So we are doing d of t by v by dv. So it is t by v at the second point minus t by v at first point by v2 minus v1. Now what we are taking between first and the last point. First and the last point. So t by v of the last point is 2769.23 and this is 1500. So we are substituting 2769.23 minus 1500. And last point is 0.65 and the first one is 0.2 in terms of volume. So again we are substituting 0.65 minus 0.2. Now if we do this, we will be getting d of t by v by dv. So we will get the slope. And if we do the calculation, I'll just calculate it once again. 2769.23 minus 1500 divided by 0.45. That is 2820.51 seconds by meter power 6. How it is meter power 6? It is t by v divided by v. So it becomes t by v square kind of. So t by v square is, t is seconds, v square is meter cube into twice. So it becomes meter power 6. And this is slope. Now after finding out slope, what we need c. So how can we know get cc is equal to this one? We can, now we know y1, m and x1, so we can take it to the other side. So y1 minus mx1. So y1 is t by v1, or else we can put it together. T by v1 minus of slope into v1. v1 is the volume, that is x1. So t by v is 1500 minus slope we have calculated as 2820.51 into v1. v1 is what? v1 0.2. So here v1 is 0.2. So that gives us 935.90 seconds by meter cube. How are we saying the units of intercept? It is t by v. Basically it has the unit of t by v. So it is seconds per meter cube. So that is how we are calculating the slope and the intercept. So once we know the slope and intercept, if we are asked to find the specific cake resistance or filter medium resistance, we can substitute it back in this particular formula and get the desired result. So that is how we do this. So I'll repeat the question once again. So what we are doing is, we are in the question, it is given that we have a leaf filter whose area is 1.2 meter square and it is having a constant pressure drop of 300 kilopascal, and it is producing the following results. So we are having time and the volume of filtrate collected with respect to the time. So now we are asked to find the slope and the intercept, which can be further used for the analysis of specific cake resistance and filter medium resistance. So what we are doing, we are just first writing out the formula. So filtration at constant pressure, the integrated form of the filtration equation is T by V is equal to mu alpha CV by 2A square delta P plus mu into Rm by A into delta P. So here T is time, V is the volume of filtrate collected, mu is the fluid viscosity, alpha is the specific cake resistance, C is the mass of solids per unit volume of filtrate, V is the volume of filtrate, and A is the filtrate surface area, and del P is the pressure drop, and Rm is the filter medium resistance. Anyways, so now what we are doing is, we are simply assuming that equation as y is equal to mx plus c. So t by v becomes y and v here is the x. So this becomes m apart from v, and this becomes the c intercept. So now what we have to do, plotting t by v versus v, and we can get slope from similar to the mathematical concept that we use in general. So it becomes y2 minus y1 by x2 minus x1. So y here is t by v. So t by v2 minus t by v1 divided by v2 minus v1. So if we are doing a normal calculation, we can like plot it in the x graph or in Excel and get the slope and intercept through graph. But since it is like we are using 2 points, we are taking the first and the last point and calculating the slope using y2 minus y1 by x2 minus x1. And later for intercept, what we are doing is, we are taking c is equal to y1 minus mx1. So y1 here is t by v1 and minus slope into v1. So that is how we get the slope and the intercept for this particular question. So I hope it is clear. Now we will go to question 2. Calculate the time required to collect 1.5 meter cube of filtrate during filtration of the same slurry at constant pressure drop of 400 kilopascal. Report your answer in minutes. So what we are asked? We are asked to find out how much time required to collect 1.5 meter cube of filtrate during filtration of the same slurry at a constant pressure drop of 400 kilopascal. So in the previous question, what we were given t values and we were given v values. So now here we went up to 0.8. So in the question it is asked that what will be the time required to collect 1.5 meter cube. So for 0.8, some slight modification. This is not 0.8, this is 0.65. Okay, so what will be the time required to collect for 1.5? So 0.65, we are taking 1800 seconds. So now what we have to do, we have to go in the reverse. But before that, in the previous question, it was the pressure drop of 300 kilopascal. Now it is the pressure drop of 400 kilopascal. So if it was 300 kilopascal, we can directly use the slope and the intercept concept and get the time required for 1.5 meter cube. Now we directly do not know the slope and the intercept, so we have to calculate the slope and the intercept at 400 kilopascal first, and then move to finding out the time required to collect 1.5 meter cube of the filtrate. So now what we are going to do is, first let us write given is 1.2 meter square, and volume of filtrate also we can write. Is equal to 1.5 meter cube. And pressure 1, that is in the question 1 it is 300 kilopascal, and pressure 2 it is 400 kilopascal. The new condition is 400 kilopascal. So from the previous calculation, what did we find out? Slope 300 is equal to 2820.51 seconds per meter power 6, and intercept we found out as 935.9 seconds by meter cube. So slope and intercept both we found out in the previous problem, and we are taking that value to the present condition. Now what we have to do? For constant pressure filtration, slope intercept relate as, here it won't come, we won't come. Okay, T by V is constant pressure filtration. The equation which we have is T by V is equal to mu alpha C V by 2A square delta P plus mu into R M by A into delta P. So now for slope and intercept, we can take slope is equal to mu alpha C divided by 2A square delta P. V won't come because V is the x. Y is equal to mx plus C is the mathematical relation, so x we should not take, so v is not taken, and in C is the intercept, which is mu rm by a into delta p. So I hope you people are able to imagine what I am saying. So in general, y is equal to mx plus c. What we say, y is equal to, okay, y is equal to x is straight line, which is like having the same. So if y is equal to x, line looks like this. For example, let us take this as 70th unit, and this will also be 70. And if we take somewhere in between, it is 30. If x is 30, y also will be 30. So the line, the graph looks something like this. Other y is equal to mx is, it can be like this, or it can even be like this if slope is 1, that is m is 1, or it can be like this. So depending on the slope, the line may go towards x or deviate away from x. So that is the y is equal to mx. But in all these, the graph starts at the origin. So basically y is equal to mx, these lines are. So if x is 0, y is also 0. We've observed certain cases wherein we have graphs of this type, where we have some small height. So this is known as intercept. So here y is equal to mx plus c. This line is of that form. Why? Because when x is 0, that is x is at the origin 0, y is not 0. It is having some residual value. That is what we call as intercept. So if we put y is equal to mx plus c, and if x is 0, y is not 0, rather y is c. So that height is what we call as c, or the intercept. So that is the relation between these mathematical equations. So now T by V is equal to mu alpha C V by 2A square delta P plus mu Rm by A delta P. So here T by V is the y and V is the x, and mu alpha C by 2A square delta P is the slope, and this is the intercept. So slope intercept can relate as slope is equal to mu alpha C by 2A square delta P. Intercept is equal to mu Rm by A delta P. So slope is inversely proportional to delta P. Intercept is also inversely proportional to delta P. If we consider rest of the things don't change much. So this is with respect to the constant pressure filtration. So slope is directly proportional to delta P and inversely proportional to delta P. So slope for at 400 kilopascal will be inversely proportional to P2. So here 2 refers to 400 kilopascal and 1 refers to 300 kilopascal. So slope at 400 is equal to slope at 300 kilopascal into P1 by P2. Here 1 refers to 300 kilopascal, 2 is 400 kilopascal. So this is subscript. So again intercept also looks like the same. Intercept at 400 is equal to intercept at 300 into P1 divided by P2. So now what is left out? We have to substitute it. That is the only thing left out to find the slope and the intercept at the new conditions, that is 400 kilopascal. So now slope at 400 is equal to, we said slope at 300 into P1 by P2. So slope at 300 we know, P1 P2 we know. So I mean it is pressure drop. So it is 2820.51 into 300 by 400. So that gives us a new slope at 400 as kilopascal as 2115.38. Next we have intercept. Intercept again we are doing the same calculation. Intercept 300 into P1 by P2. So 935.9 into 300 by 400. So we get the new intercept at the 400 kilopascal. So now we have given that volume of filtrate is 1.5 meter cube, for which we need to find the time. So what we do? Or else we can put it like 400 is 2, 300 is 1, you can put a pressure drop. So basically we can put 300,000 also to keep consistency. Now what we have to do, we need to find the time at which we collect the 1.5 meter cube filtrate. So continuing to that, time calculation is equal to slope into V square plus intercept into V. Oh, it is 400, right? That's what it is, not 500, it is 400. But anyways, I'll change it into the original interface. So how did we get this? T by V is equal to M into V plus C. So I'll write it, T by V equal to slope into V plus intercept. So in order to get the time, we can multiply slope take this v to the other side, so it becomes t is equal to slope into v square plus intercept into v. So now we are taking for the 400 kilopascal condition. So slope 2 into v square plus intercept 2 into v. So slope 2 we and intercept 2 we have calculated here. So slope 2 is 2115.38 and intercept 2 is 701.93. So substituting it here we will get okay, and then we have to substitute for V as well, volume of filtrate collected. So substituting back in there we will get the time. So the unit here will be in seconds. We need to convert it back into minutes, because in the question it is asked report your answer in minutes. So we are dividing it by 60 to get the answer in minutes. So that is how we get the solution for this problem. So I'll explain it one more time. So simple. Now in the previous problem we were calculating slope and the intercept. Now in this problem we are given a new pressure drop condition and asked to find the time required to collect the 1.5 meter cube. So here pressure drop is varying, and from 300 kilopascal to 400 kilopascal, and for the new condition we are asked to find the time required to collect 1.5 meter cube of the filtrate. So what we should do, we should first find the new slope and the intercept. For finding new slope and the intercept, I can put it one here itself. New slope is, sorry, old slope is 2820.51 and old intercept is 935.9 seconds per meters cube, which both we calculated from the previous previous condition. So volume of filtrate is 1.5 meter cubes. And after finding the new slope and the new intercept, what we are doing, we are just okay, first we are finding the new slope and the new intercept, and after finding we are just directly substituting it back here and getting the time required to collect the new sorry, new not new 1.5 meter cube of the filtrate. So that is how we do the question. So it is all basic math but with a little application in the particular context. So that is how we do question 2 as well. Now we will see question 3. The porosity of a filter medium is defined as dash. Option A, volume of solids per unit volume. Option B, volume of void space per total volume. And option C, density of the filter medium. And option D, thickness of the filter cake. So we are given 4 options and we need to find what is the exact definition of the porosity of a filter medium. So what do we mean by porosity? We just mean that the volume fraction of pores in the filter medium. So how do we get the volume fraction of pores in the filter medium? It is the volume of voids present in the filter medium to the total volume of the filter medium. So that is how we define the porosity of a filter medium. So porosity is nothing but the volume fraction of voids or volume fraction of pores in the filter medium, that is absence of anything in that space. So based on that we will get porosity of a filter medium as volume of voids per total volume. So answer is option B, the volume of void spaces per total volume. So volume of solids per unit volume, this is again volume fraction of solids. This 1 minus this will give us the option B, but this is not the right answer. So B is the right answer, and C and D are again density of filter medium, thickness of filter cake, those are not the right answer. So this is for question 3. Now we will go to question 4. So in question 4, select the appropriate choice for column A from column B. So what do we have in column A? We have Ergun equation, we have Hagen-Poiseuille equation, we have a Bernoulli equation, we have Stokes law. On the column B, what we have is tube flow, cross flow filter, packed bed, overall energy balance, sphericity and settling. So select the appropriate choice for column A from column B. So first we'll see what is there in column A and we'll match it with column B. First one is Ergun equation. So Ergun equation is used for finding the pressure drop inside the packed bed. So option A we can go with 3, and second one is Hagen-Poiseuille equation, which is like used in the tube flow, and third one is Bernoulli equation. So Bernoulli equation is used for overall energy balance, and finally we have Stokes law. In Stokes law we use it for settling in the low Reynolds number region, but Stokes law is used for the settling study. So we'll see the options and we will finalize the answer. So option A, it is A3, B1, C4, D6. And option B, it is A2, B3, C4 and D1. Option C, it is A1, B2, C3 and D4. Option D, it is A4, B2, C5 and D6. So answer we have discussed. Ergun equation is for packed bed A3, B1 and C4 and D6. So answer is option A. So this is only matching with our answer. So answer is option A. In the next slide we will see more about it. And I'm just putting a comma to separate because it is quite difficult to see without any division between them. So but answer remains same. A is 3, that is Ergun equation is for packed beds, and B is Hagen-Poiseuille equation is for tube flow, and C Bernoulli equation for overall energy balance, and D Stokes law is for settling. So we'll see the explanation now. So the Ergun equation describes a pressure drop across a packed bed of particles. It combines both viscous and inertial effects in a packed bed, which is fixed arrangement of solid particles through which fluid flows. This equation is widely used in chemical engineering for packed bed reactors or filters. And second we have Hagen-Poiseuille equation. The Hagen-Poiseuille, okay, I wrote it wrong. The Hagen-Poiseuille equation applies to laminar flow of a viscous fluid in a long circular pipe or tube. It relates the volumetric flow rate to the pressure difference, fluid viscosity and tube dimensions. So it is specifically used to describe tube flow of fluids. And third one, it is Bernoulli equation. So the Bernoulli equation is a statement of conservation of energy for flowing fluids. It relates pressure, velocity, elevation along a streamline representing an overall energy balance of fluid flow. And last one, it is Stokes law. Stokes law describes the drag force experienced by small spherical particles moving slowly through a viscous liquid. It is commonly used to calculate the settling velocity of particles under gravity in a fluid such as sedimentation or settling processes. So these are the 4 things. So now I hope, it is just a theory question, so we'll move directly to question 5. So in question 5, what is asked is, which of the following is a common filter medium? Options are option A sand, option B glass wool, option C cloth, option D all of the above. So common filter medium, actually it is all of the above is the right answer, because all can be used as the filter medium. So option D is the right answer. Now we'll go to question 6. Question 6 is again a problem, but more than this week's, it is somewhat relating with the problem we saw in the last week. A packed bed of solids of density 2.5 gram per centimeter cube occupies a depth of 150 centimeter in a cylindrical vessel of inside diameter 15 centimeter. The mass of solids in the bed is 25 kg and the mean diameter of the particles is 0.09125 mm. Water density 1 gram per centimeter cube and viscosity 0.001 pascal second flows upwards through the bed. What is the voidage of the packed bed? So what is given? We are given that we have a packed bed and it has solids whose density is 2500 gram per centimeter cube, or sorry, 2.5 gram per centimeter cube, and its actual density is 2500 kg per meter cube in the SI units, and it occupies a depth of 150 centimeters. So the height of the packing is 150 centimeter and it is in a cylindrical vessel whose inside diameter is 15 centimeter. So 15 centimeter diameter column with 150 centimeter height, and mass of solids in the bed is 25 kg. So with mass, we can like say how much quantity of particles inside the bed. We can even calculate the volume occupied by the solids in the bed, and the mean diameter of the particles is 0.09125 mm, and water flows through the bed, and what is the voidage of the packed bed? So we need to calculate the voidage. So similar to how we did in the last week, voidage of the packed bed is equal to void fraction of the packed bed, or it is volume of voids in the bed divided by the total volume of the bed. So how can we know the volume of voids? Volume of voids is nothing but volume of empty space. So it can be 1 minus the volume of solids in the bed to the volume of the bed. So that is 1 minus the solid volume fraction inside the bed. So that is how we do. How to get the volume of solids inside the bed? We know the mass of solids inside the bed and we know the density of solids inside the bed. So based on those two, we can get the volume of solids inside the bed, and volume of the bed we can calculate by using the dimensions given. That is, its depth of the bed is given and in the diameter of the bed is given. So with both of that information, we can calculate the volume of bed. So we'll start the solution. So given density of solids is equal to 2.5 gram per centimeter cube. So it is 2500 kg per meter cube. Cylindrical vessel depth is 150 centimeters, or in, I am just writing everything in meters or in SI units. So here it is 1.5 meters, here it is 2500 kg per meter cube. Cylindrical vessel inside diameter is 15 centimeter or 0.15 meter. Mass of solids inside the bed is 25 kg. Mean diameter of particles is 0.09125 mm, or it is 9.125 into 10 power minus 5 meter. Density of water is 1 gram per centimeter cube or 1000 kg per meter cube, and viscosity of water is 0.001 pascal second. What we need to find? We need to find the voidage of the packed bed. So voidage of the packed bed is given by epsilon is equal to 1 minus solid fraction inside the bed, that is 1 minus epsilon s. So epsilon s is the solid fraction inside the bed, solid volume fraction inside the bed. solid volume fraction inside the bed, and epsilon s is given by volume of solids inside the bed divided by the volume of the bed. So basically we need to know the solid volume fraction inside the bed. So what we are doing, we are calculating the volume fraction of solids. So volume fraction is, what is fraction? It is the fraction of that present to the whole quantity. So volume of solids inside the bed to the whole volume of the bed. So that gives us epsilon s. And volume of solids inside the bed, how do we calculate? Volume is equal to mass into density. So mass by density. Mass is equal to density into volume, and volume is equal to mass by density, not mass into density, I'm sorry. So it is mass by density. So volume of solids inside the bed is mass of solids inside the bed by density of solids inside the bed. So volume of solids inside the bed is therefore mass of solids is 25 divided by 2500. So that gives us 25 by 2500 is 1 by 100, and that is 0.01 meter cube. So it is kg by kg divided by kg per meter cube. So that gives us meter cube. Now next what we need to find? We need to find the volume of the bed. So volume of the bed is, so the column is a cylindrical column. So a cylindrical column So cylindrical column, therefore what happens? Volume of the bed is volume of the bed, that is the total volume of the bed is volume of the cylinder. So what is volume of the cylinder? It is like, you can say it like pi r square L. So pi r square L is the volume of the cylinder. Now therefore what we are doing, we are taking the diameter, so we are using pi by 4 d square L. So on substituting, we know the diameter of the column and we know the length of the column. So substituting that will give us the volume of the bed. So what, pi by 4 d square h. Pi by 4 d square h, and it is 3.14 divided by 4 into diameter is 0.15 meter into h is 1.5 meter. So using that, what we can get is 3.14 divided by 4 into 0.15 square into 1.5. So we will get 0.02649, so 0.0265, and this is 0.01. So volume fraction of solids inside the bed is therefore 0.01 divided by 0.0265. So that gives us 0.3774. So volume fraction of solids inside the bed is 0.3774, and therefore we can tell that 1 minus 0.3774, that is 0.6226 is voidage of the packed bed. Generally what happens is that voidage won't be this high. Packing fraction itself will be 0.6. Voidage will be voidage will be like 0.4, something like that. That too for spheres and all, we can take it around 0.62 as the packing fraction and 0.38 as the void fraction. So here as I mentioned before or in previous classes also, since I am changing values, it is kind of giving an extra value, but other than that, don't think voidage will be this high. Voidage will be, otherwise I'll mention high voidage. So that is for question 6. Now we will go to question 7. Question 7 is, calculate the superficial liquid velocity at which the pressure drop across the bed is 103 to 10,325 Pascal. Report your answer in mm per second. So what are we asking? We are asked to find the superficial liquid velocity at which the pressure drop across the bed is 10,325 Pascal. Okay, pressure is again very low. Pressure drop is low. Okay. Yeah, okay. This is pressure drop, right? So not low. Pressure drop is correct only. We have to find the superficial liquid velocity at which the pressure drop across the bed is this. So we are given the pressure drop. We know the bed is packed bed, so we can use the Ergun equation and find the answer. So solution, what is given? Pressure drop across the bed is given as 10,325 Pascal, and we have to find the superficial liquid velocity. So as I mentioned, we can use the Ergun equation to find the pressure drop across the packed bed. So I didn't mention this Ergun equation. Ergun equation. So Ergun equation is given by delta P by L equal to 150 V mu into 1 minus epsilon square divided by phi square dp square into epsilon cube plus 1.75 into rho V square into 1 minus epsilon by phi dp into epsilon cube. So this is like for the mostly applicable in the laminar condition, and this is in the turbulence condition, but since we don't know, we can take both and we'll get the solution. So now in this question, what do we know? Delta P we know, length of the bed we know, V is unknown, mu is water, so we know, epsilon we found out in the previous problem, and diameter of the particle is also given in the question, and epsilon we found out, and rho is 1000 kg per meter cube for water, and rest all the things we know. Phi is 1, assuming the particles to be spherical. So what are we doing? We are substituting everything in the equation. So it is delta P is 10325 divided by 1.5 meter of the packed bed equal to 150 into V into mu. Mu is 0.001 into 1 minus epsilon. Epsilon we found out in the last problem as 0.6226, and divided by phi is 1, dp is 9.125 into 10 power minus 5 whole to the power of square divided by into 0.6226 to the power of 3 plus 1.75 into 1000 into v square into 1 minus 0.6226 divided by 5 into dp. So 5 becomes 1 and dp is 9.125 into 10 power minus 5 into epsilon cube 0.6226 to the power of 3. So this is the equation. So what have we got here? We got this, we got v, we got v square. So now we will simplify the equation, and what will we get? We just make all the calculations mentioned over here. So it becomes 10325 by 1.5 becomes 6883.33, and simplification of this will give us this number into v plus simplification of this will give us this one into v square. So what form this is x square ax square plus bx plus c. I'll show you again, Xbox. So a x square plus bx plus c equal to 0. So what is the solution for this? X is equal to minus b plus or minus square root of square root of 1 minus b square and b square by 4ac divided by 2a. I'll just verify this, just give me a minute. Oh, sorry. B square minus 4ac. Sorry. I'm sorry, it is wrong. That's what I was thinking, something was wrong. B square minus 4ac by 2a. ax square plus bx plus c is equal to x is equal to minus b plus or minus b square minus square root of b square minus 4ac whole to the power whole divided by 2a. Actually this is whole. So we can actually calculate using this and we will get the final b as 6.4626 into 10 power minus 4 meters per second, or it is equal to 0.6463 mm per second, because in the question it was asked give the answer in mm per second. So that is why we are giving the answer in mm per second. So apart from this, I'll show you another way to find the solution. I am not sure whether you know how to do this using scientific calculator or not. Many of them may be knowing, but if you are not knowing, I'll just show how to get the solution for the equation using the scientific calculator. So what you need to do is you need to take the calculator and there will be some option like mode, clear, on, like near the on button the next button will be mode. If you press that once, you will have a lot of options, and so you need to press it 3 times, or like press the mode button repeatedly till you get one option as like equation EQN MATVCT, like that you will get one option, and below that EQN you will have 1. So this you have to press 1, and after that it will ask unknowns questions 2 and 3, and if you press the side button you will have degrees and it is 2 and 3. So now what we are doing is we are solving for the degrees. Ax square plus bx plus c. So here degrees is 2. So if we are going for cubic equation, it will be ax cube plus bx square. So that time we should give degrees as 3. But right now our degree is 2. So degree we need to press 2 and it will ask for A. So A here is 299760001.22 and next it will ask B question. So that time we need to press 10631681.44 and C it is 6883.33. So it is ax square plus bx plus C. C is minus 6883.33 and after that if we press equal to, we will get x1 value. X1 is B. So it is, so basically it will be like minus B plus or minus, right? So one will be your solution, the other will be negative, right? So based on our context we have to choose a solution, and since it can be negative we are going with the first one. So it is 6.4626 into 10 power minus 4 and other one will be minus 0.355, so which we don't want. So that is also how you can get the solution directly using the scientific calculator. So here I'll tell you one more time. Take your scientific calculator and it is what I am using is Casio FX991MS. So depending on which model you are using, settings may slightly differ. What you need to do is, there will be a mode MODE button which you need to press and you just keep on pressing till you get EQN, that is equation. So till you get that, keep on pressing, and below that EQN you will have one number. That number you press, and after that you will have two options, unknowns, and if you press the side button you will get degree. Side button is the round button where you can go any direction. So in the degree, if you press here, our degree is 2, so we have to press 2, and later we need to give A and press equal and give B, press equal and give C and press equal. You will have the final answer. So once you get the final answer, how to exit is that, so again in the same mode button you will have one more option like clear, CLR. So to get that you need to press shift because it is in a different color. CLR will be in different color in most of the calculators. So press shift and press CLR. You will have three options, MCL, mode and all. So in all, under all you will find number 3. So if you press 3 now, you can reset everything. Press 3 and give equal. So you can exit from the equation mode. So to exit from the equation mode, you need to press that clear. So for that you press shift and you press CLR and give all. So it is like that. So it is one of the easy way to get the solution, because you can't like do this ax square plus bx plus c all the time. So if calculator is permitted, you can use this. So that is one of the ways. And okay, we'll take a 5 minutes break actually. Time is 4:05. We will come back by 4:10. Okay, we'll start now. So now in question 8, what is asked is, corresponding to these conditions, what is the actual velocity of the fluid flowing through the packed bed? So what is asked? We have to find out what is the actual velocity of the fluid flowing through the packed bed, and we are asked to report our answer in mm per second. So we calculated the superficial velocity in the previous question. Now we have to find the actual velocity. So actual velocity is equal to superficial velocity divided by the void fraction. So superficial velocity is also known as the empty tower velocity. So now we are actually finding the actual velocity of the fluid flowing through the packed bed. So we are dividing it by the void fraction. So to find actual velocity of the fluid and solution, how to do, actual velocity is equal to superficial velocity divided by the void fraction epsilon. So superficial velocity, which we calculated in the previous previous is 0.6463, and void fraction we calculated before that as 0.6226. So we substitute both of them here. So it is 0.6463 divided by 0.6226. That gives us the answer 1.0381 mm per second. So that is how we calculate the answer. Now we will go to next question, 9th question. In 9th question, what is given is that a leaf filter has an area of 2.5 meters square and operates at a constant pressure drop of 400 kilopascal and produces the following results during a test on filtration of a slurry. So similar to question 1, but numbers are changed. So time is given, and similarly it starts from 300 seconds and it goes on for every 300 seconds. So 300, 600, 900, 1200, 1500 and 1800. So it starts from 5 minutes and it ends at 30 minutes. And volume of filtrate collected in the corresponding time is given. So it is 0.2 meter cube, 0.3 meter cube, 0.4 meter cube, 0.5, 0.6 and 0.7. So now assume the cake is incompressible. Evaluate the slope and intercept required for the calculation of specific cake resistance and filter medium resistance. So first, again, like in the previous problem, I'll just times okay. So basically, I just want to like. Yeah, since it was occupying more space, I just want to reduce the space. So when analyzing filtration at constant pressure, the integrated form of the filtration equation is T by V is equal to mu alpha CV by 2A square delta P plus mu into Rm by A into delta P. So T is the time, V is the filtrate volume, mu is the fluid viscosity, alpha is the specific cake resistance, and C is the mass of solids per unit volume of the filtrate, and delta P is the pressure drop, A is the filter surface area, and Rm is the filter medium resistance. This is all things similar to the last what we discussed in question 1. Now what we need to find? We need to find the slope and the intercept. So again, T by V versus V, when we plot, we will get the slope and the intercept. Slope and the intercept. and using that slope and intercept we can find the specific cake resistance and filter medium resistance, that is alpha and Rm we can find. So first plotting T by V versus P, similar to that which we saw y is equal to mx plus c. So slope will be y2 minus y1 divided by x2 minus x1. So we are taking similar to that first and the last point. So m is slope, which is this is time, this is volume, and this is T by V in seconds per meter cube. So we are dividing this by this. 300 divided by 0.2 will be 1500. 600 divided by 0.3 will be 2000, and again 900 by 0.4 it is 2250, and 1200 by 0.5 it is 2400, and 1500 by 0.6 it is 2500. Oh, 1500 by 0.6 is 2500, and finally 1800 divided by 0.7 it is 2571.43. So this is in seconds per meter cube. So we are taking the first one and the last one. This is 1500 and 2571.43. 2571.43 minus 1500 divided by 0.7 minus 0.2. 0.7 minus 0.2, and that will give us 2571.43. 2571.43 minus 1500 divided by 0.5, that is 2142.86 seconds per meter power 6. Now how do we calculate the intercept? For intercept we can calculate it using y equal to mx plus c. So c is equal to y minus mx. So y is T by V, so it is whole, and minus slope into V1. So slope we found out as 2142.86 into V1. V1 is 0.2 and T by V1 at that condition is 1500. So it is 1500 minus 2142.86 into 0.2. What are we getting? Minus 1500 will be 1071.428 or 1071.43 seconds per meter cube. That is the intercept. So intercept will mostly have the unit same as y, so it is seconds by meter cube. So that is how we calculate the slope and the intercept for this particular problem. Now we'll go to question 10. In question 10, what are we asked? A similar problem to the last problem. Calculate the time required to collect 2 meter cube of the filtrate during filtration of the same slurry at a constant pressure drop of 500 kilopascal. In the previous question, the pressure drop was 400 kilopascal. In this question, the new condition is 500 kilopascal. And what will be the time required to collect 2 meter cube? So here we went up to 0.7 meter cube with the 400 kilopascal. Now if pressure drop is increased to 500 kilopascal, what will be that? So that is the question. So we'll write what is given first. It is 2.5 meter square area, and subscript 1 refers to 400 kilopascal condition. Kilopascal condition, and subscript 2 refers to 500 kilopascal condition, and P1 is 400 kilopascal, P2 is 200, for 500 kilopascal. So it is slope 1 and intercept 1 is therefore 2142.142.86, which we did calculate from the previous problem, and intercept is similarly 1071.43, which again we calculated from the previous problem. From previous question calculation we can find it this. 1142.86 and 171.43. So now we have to first find the new slope and the new intercept. So by now we know slope is inversely proportional to delta P. Okay, we'll add it here. So I'm just changing the notation because it is quite confusing, so that's why I am changing. So what we should add is, we should add a symbol. So it is delta, slope is inversely proportional to delta p. Similarly, intercept is also inversely proportional to delta p. So slope 2 into delta p2 is equal to slope 1 into delta p1. And so slope 1 we know, delta p1 we know, delta p2 we know. So it is 2142.86 into 400 divided by 500, which gives us the new slope 2, which is 1714.29 seconds per meter 6. And intercept 2 is equal to intercept 1 into delta p1 by delta p2. Again it is 1071.443 into 400 by 500, which gives us 857.144 seconds per meter cube. Now we found out the new slope and the new intercept. Now we have to find the time required for collecting the filtrate volume of 2 meter cube. So how to calculate? Time calculation is equal to slope into v square plus intercept into v. So how it is? T by v is equal to slope into v plus intercept. So from that, t is equal to slope into v square plus intercept into v. Again it is not 500 which we are using, it is 2. So intercept 2 and slope 2 we found out. So slope t is equal to 1714.29 into 2. New, the filtrate volume for which we need to calculate the time is 2. So it is 1714.29 into 2 square plus 857.144 into 2. So it is the calculation right? 14.29 into 4. Okay. 857.144 into 8571.448. So 8571.448 seconds. If we calculate it to minutes, we will get it as 142.8575 minutes. So what was the unit which was asked in question? We are asked to find it in minutes. So the answer is right. So what did we do? We in the previous problem we found out slope and intercept. So now the pressure drop condition is increased to 500 kilopascal. So first we need to find the slope and the intercept for the new condition. So slope and intercept both are inversely proportional to the pressure drop. Based on that, we found out the slope and the intercept values at the new condition. And by using the slope and the intercept, we can calculate the volume. We can calculate the time for which we need to wait to get the filtrate. So it is 142.8575 minutes or 8571.448 seconds. This is 2 meter cubes. If we go back and see the question itself, we can say that for 0.7 the seconds is 1800. So it is like, since it is a constant pressure, with increase in time there will be a lot of buildup of the solids as well. So based on that only we are finding. So that is for question 10. Now we will go to question 11. A bed of ion exchange beads 243.84 centimeter deep is to be backwashed with water to remove the dirt. These particles have a density of 1.5 gram per centimeter cube and an average size of 1.5 mm. What is the minimum fluidization velocity using water and assuming the density of water to be 1 gram per centimeter cube and viscosity to be 0.001 Pascal second? The beads are assumed to be spherical and the porosity at the incipient fluidization can be taken as 0.45. And we need to report the answer in mm per second. So what is asked? We are asked to find the minimum fluidization velocity when we have a packed bed with the solids whose condition is given, and we are also given the porosity at the incipient fluidization as 0.45. Now we have to find the minimum fluidization velocity. So we'll see how. First let us write the given. Bed depth is 243.84 centimeter. Density of particles is given as 1.5 gram per centimeter cube, and size of the particles is 1.5 mm, or it is 1.5 into 10 power minus 3 meter. We are writing everything in SI units. And density of water is 1 gram per cc, or 1000 kg per meter cube, and viscosity of water is 0.001 pascal second, and shape of the particles is given as spherical. Porosity at the incipient fluidization is given as 0.45. So these are the given. Now we need to find the minimum fluidization velocity. So for that, if it is a packed bed, what is the equation we use? It is delta P by L is equal to 150 into V into mu into 1 minus epsilon the whole square, 1 minus epsilon square divided by 5 into dp the whole square divided by epsilon cube, plus 1.75 rho V square into 1 minus epsilon divided by 5 dp into epsilon cube. So this is for the packed bed condition. Now the bed is moved to minimum fluidization condition. So at that point, what happens to delta P is that delta P becomes rho P minus rho into G into L into 1 minus epsilon. So now we are substituting this back in the equation. So that becomes rho P minus rho into G into L into 1 minus epsilon is equal to, the rest all the things remain the same. So now what we can do, this L and this L gets cancelled basically, so we need not substitute the value. So rest of the things we can do, 1500 minus 1000 into 9.81 into L into 1 minus 0.45 divided by L. L gets cancelled, so even if we substitute values it doesn't matter, and equal to 150 into V into 0.001 into 1 minus 0.45 square divided by phi is 1, because phi is the sphericity. So here it is given particles are spherical. So if the particles are spherical, phi is 1. And therefore we have only dp. dp is 0.0015 square into epsilon cube. Epsilon is 0.45 cube. Plus 1.75 into 1000 into v square into 1 minus 0.45 divided by 0.0015 into 0.45 cube. So after that again we are calculating and simplifying this particular form into this particular form, wherein we have a quadratic equation. So it is 7416.09.51 v square plus 2, not 7000, it is 70,41,609.51 v square, and this is 2,21,307.73 v equal to 2,697.75. So again, like, we can use either x is equal to minus b plus or minus p square, square root of p square minus 4ac by 2a formula, or we can straight away calculate using the calculator approach, scientific calculator. It is a scientific calculator. So that approach which I have shown last time. If you are familiar, most people will be familiar. So if I just said for those who might not know, so you can calculate it using that as well. So finally what we will be getting is 9.3866 into 10 power minus 3 meter. So since we are, okay, it is not meter, actually it is meter per second. This is in mm per second. So that matters. So I'll just check if I did any equation wrong in the previous. I'll just check and come. Okay, in all other things equation is right only. Okay, that is for question 11. Now let us see few theoretical questions. I think I should mention for packed bed. All right. Yes. Or L also we can substitute, it is 2.4384 meter, and when it goes there it becomes 2.4384. Yeah, and that's it. Now we will see few theory questions. Just a straightforward questions only, not a complicated one. Question 12. A filter aid is used to. Filter aid is used to. Option A, increasing the viscosity of the fluid. Option B, decrease the particle size of solids. Option C, improve the porosity and the permeability of the filter cake. Option D, chemically react with the solids. So what we do, during filtration and all, we use the filter aids, right? So why do we use filter aids? That is the question. So answer is actually option C. So it is used to improve the porosity and the permeability of the filter cake. So what they do is, it is widely used to remove the impurities which tend to clog the filter medium. So it is continuously dosed to the suspension to be purified. So it is like a granular or fibrous substance. So like diatomaceous earth, perlite cellulose, that is added during the filtration to create a porous, rigid and permeable filter cakes. So this improves the filtration efficiency also. So that is why we use filter aids. So answer is option C. Improve the porosity and the permeability of the filter cake. So that is answers to question 12. So for question 13, we have, in constant pressure filtration, the filtration rate remains constant throughout the process. Option B, increases with time. Option C, decreases with time as the cake builds up. Option D is independent of cake thickness. So in constant pressure filtration, the filtration rate dash. So in constant pressure filtration, what happens is that the filtration rate actually decreases with time as the cake builds up. So answer is option C. So how we will see now. In constant pressure filtration, what happens is that the pressure difference across the filter is kept steady. That's why it's constant pressure, right? So it is used for the simplified process, not anything else mostly. Or in generally simple problems we use that, not in complicated systems. Initially, when the filter cake is thin or absent, the fluid flows relatively easily, so the filtration rate is high. As the filtration proceeds, solids accumulate on the filter medium, forming a filter cake, and this cake adds resistance to the flow, making it harder for the fluid to pass. Since pressure is constant but resistance increases due to cake thickness, the filtration rate decreases over time. So that is what happens. So basically, in constant pressure filtration, what happens is that resistance increases the filtration resistance increases, and due to that, like because of the cake thickness which keeps on accumulating over time, and because of this the filtration rate decreases over time. So option C is the right answer. So now finally we have question. Okay, this relationship is often described by the Berg's equation or derived from Darcy's law for flow through porous media. So we'll now go to question 14. Okay. In question 14, what is asked is that depth filtration is characterized by dash. Solids being trapped on the surface of the filter. Option B, solids being trapped within the filter medium. Option C, filter medium being replaced frequently. Option D, use of vacuum pressure only. So what is depth filtration? What is characterized by it? A solid being trapped inside the filter medium. So answer is option B. Solids being trapped inside the filter medium, and we'll see a quick explanation for that. Depth filtration involves a thick filter medium, that is a sand bed fibrous material, where solids are captured within the interior of the filter material, not just on the surface. So mostly if we use filter cloth and all, the solid material captured will mostly be on the surface. So here in depth filtration, it involves a thick filter medium where solids are captured within the interior of the filter material and not just on the surface. The solids penetrate and get trapped inside the porous matrix due to mechanisms like interception, diffusion and sedimentation. This differs from the surface filtration where particles are retained on the surface of the filter medium forming a cake. Depth filters are used for removing small or suspended particles from fluids over a large medium and are common in water treatment. So what happens in depth filtration? The solids penetrate and they get trapped inside the porous matrix due to mechanisms like diffusion, sedimentation, interception. So this is different from the surface filtration where particles are retained on the surface of the filter medium and they form a cake. Mostly with cloth which we observe, like in home and all we use cloth to filter, right? Like in cooking and all we use those things. So that is surface filtration, whereas in depth filters what they are used for removing small or suspended particles from fluids over a large volume and are common in water treatment. Mostly like in uh, previously we used to have sand filters, right, wherein sand will be filled and the water will be allowed to pass through it, and like it will remove any small or suspended particles. So that is the depth filter which we might have seen in our younger ages. They often allow higher dirt holding capacity before clogging compared to surface filters. Surface filters get clogged very easily, whereas um, depth filters have a comparatively larger dirt holding capacity. Like their capacity is quite high. So that is for question 14. Now let us see for the question 15. In question 15, what is asked? Backwashing in filtration is performed to dash. Increase fluid velocity through the filter. Option B, remove accumulated solids from the filter medium. Option C, increase filter cake thickness. Option D, reduce fluid viscosity. So in general, mostly we perform backwash in filtration process. The question is about why do we do the backwashing in filtration process. So backwashing is a filtration mechanism maintenance process actually, like wherein we reverse the flow through the filter bed and to clean it or dislodge the accumulated particles and the contaminants. So basically it is for removing the accumulated solids from the filter medium. So answer is option B. So where what happens in backwashing is that remove accumulated solids from the filter medium. So what happens is that we use a high velocity flow of water, and so thereby the filter media, it it gets kind of fluidized, and we expand the bed and flush out the trapped solids in that. So why do we do? We do it to restore the filter's efficiency and permeability. So so we do that to prevent the accumulation of solids in the filter medium. So that is the case. The answer is option B. Now we'll see question 16. Minimum fluidization velocity UMF is defined as dash. Okay, sorry. Minimum fluidization is defined as dash. Where does the minimum fluidization concept come? It comes in the fluidization. So what happens in fluidization is that we pass the fluid inside the packed bed and we allow the particles to fluidize it. That is like we allow the particles to move, and like the particles starts behaving like a fluid. That is what is called as fluidized bed. So when packed bed, we keep on increasing the velocity till a certain point the particles do not move, after which the particle starts to move. So the point at which the bed stays suspended is known as the minimum fluidization condition or incipient fluidization. At that condition the particles just keep floating and they do not move actually. So minimum fluidization is defined as, okay, we'll see the options first. Option A, the velocity at which the fluid stops flowing. Option B, the velocity at which the drag force balances the weight of the particles in the bed. Option C, the velocity at which particles settle to the bottom. Option D, the velocity at which the bed compacts fully. So minimum fluidization velocity is defined as the velocity at which the drag force balances the weight of the particles in the bed. So option B is the right answer. So what happens in minimum fluidization? So the particles stay suspended. So because of that, they neither move, they neither stay closely packed as is the case in the packed bed. So the velocity at which minimum fluidization velocity is the condition velocity at which minimum fluidization condition is achieved. So at minimum fluidization condition, what happens? The drag force just balances the weight of the particles. So the particle stays suspended in the bed, but they are not expanding or moving as in the fluidized bed, but they are also not compactly packed condition as in the packed bed. So that is the case. So option B is the right answer. The velocity at which the drag force balances the weight of the particles in the bed. Option B is the right answer. So question 16 is that. Now let us move on to question. Okay, I just want to remove this. We are almost towards the end actually. We have only I think 2-3 problems left. Okay, we'll go to question 17. Question 17. At fluidization point, the pressure drop across the bed. Option A is 0. Option B equals the weight of the bed per unit area. Option C decreases with increasing velocity. Option D is independent of bed height. So what happens is that at a fluidization point, the pressure drop across a bed is dash. So if you remember this graph actually, in below at the packed bed condition, with increase in the velocity, the pressure drop across the bed increases. But at the fluidization point, the pressure drop across the bed equals the weight of the bed per unit area. Similar to the last question where we saw about the drag force equaling the particle weight, here it is the same. At fluidization point, the pressure drop across the bed equals the weight of the bed per unit area. So option B is the right answer. It is not 0, it doesn't decrease with increasing velocity, it is not, after fluidization the pressure drop across the bed remains almost constant, and it is independent of bed height is also not the right option. So answer is option B, equals the weight of the bed per unit area. So option B is the right answer. So now let us go to question 18. In fluidized bed, the void fraction is generally dash. Option A equal to 0. Option B less than the porosity of the packed bed. Option C greater than the porosity of the packed bed. Option D equal to particle volume fraction. So in a fluidized bed, what is asked? Void fraction is asked. Void fraction is the like empty spaces in the bed. So in fluidized bed, actually the bed height expands. If height expands, what does it mean? It means that the void fraction is expanding. Void volume is expanding. So because of that, the porosity is higher than in the packed bed kits. Because in packed bed, the height is fixed, so it is compactly packed. Whereas in fluidized bed, the height is increasing. Therefore, the same volume of solids which occupied a very less height in the packed bed is now occupying a very large height. So obviously, the porosity or the void fraction will be high. So void fraction is generally greater than the porosity of the packed bed. So option C is the right answer. In a fluidized bed, the void fraction is generally greater than the porosity of the packed bed. I hope you are able to imagine or visualize that thing, that the void fraction in the packed bed is generally lower than the void fraction in the fluidized bed. Why? Because the height the particles occupying in the packed bed is generally lower. In the packed bed it is fixed, whereas in fluidized bed it is keeps on increasing with respect to the regimes of fluidization. So answer is option C, greater than porosity of the packed bed. And question 19, we have what happens when fluid velocity exceeds the terminal velocity of a particle in a fluidized bed. So terminal velocity is the velocity at which the particle starts to like settle or move back. When fluid exceeds the terminal velocity, what happens? It will carry away the particle. The particle won't be settling anymore. Rather, they will be entrained in the bed. They will be carried by the fluid along with the bed. So option A, the bed compacts further. Option B, particles are carried out of the bed entrainment. Option C, bed height decreases. Option D, fluid velocity decreases. So the right answer is the particles are carried out of the bed, that is entrainment happens when the fluid velocity exceeds the terminal velocity of the particles in the fluidized bed, because after which the particles cannot settle, so therefore they will be carried away from the out of the bed. The velocity is that high, that is the concept. So answer is particles are carried out of the bed. So now let us go to question 20, last question for today's session. Which equation is commonly used to estimate pressure drop in a packed bed? Again, it is a very simple question which we know in a packed bed we use Ergun's equation to estimate the pressure drop inside the bed. So options given are option A, Bernoulli equation, Option B, Hagen-Poiseuille equation. Option C, Ergun equation. Option D, Stokes law. So which equation is commonly used to estimate pressure drop in a packed bed? So answer is option C, Ergun equation. So we use Ergun equation to estimate the pressure drop in a packed bed. So this question is kind of similar to question 4 where we matched between column A and B. So that is for question 20. So yeah, thank you for attending today's session. Now if you have any doubts, we'll discuss. So in today's class we saw problems involving fluidization and filtration. So if you have any doubts in those topics or any other topics also, you can ask. Now we'll discuss. If okay, if there are no doubts, we'll close this session. I am closing the session. These recordings and PPTs will be available to you. So we'll see. Okay, we'll see. Thank you for attending today's session. We'll meet again next Saturday, same timing, 3 to 5 p.m. Yeah, thank you.